Hello, my name is Álvaro Rivas, and I am an ISO ALMA Fellow in Chile. And in this talk, I want to give you a brief overview of the type of science that you can do with ALMA if you work on planet formation and protoplanetary disks. So planet formation was one of the main science goals when building ALMA. The idea is that ALMA would be able to resolve scales of a few astronomical units in protoplanetary disks at the distances of nearby star-forming regions such as Taurus or Ophiuchus. So here we have two observations of the pre-ALMA era. Those were considered high angular resolution observations at the time. If you're not familiar with interferometry, those white ellipses, that's the beam of these observations. That's the resolution element. So we can see that the disks are resolved and they seem to be smooth. This is what we thought disks looked like for some time. But then ALMA came around and delivered these observations for these systems. You can see the dramatic improvement in angular resolution, and also that these disks are not smooth anymore. These type of systems of gaps and rings are found on almost every disk that is observed with sufficient resolution. So ALMA is really changing the field of planet formation. This is the type of data that you can get if you observe with ALMA. And ALMA is also extremely flexible. When you observe with ALMA, what you get is cubes, which is a collection of images at different frequencies. So if you're interested in the continuum emissions, you can just combine all those images, those channels, to boost the signal-to-noise ratio of your observation, and you get a continuum image. And if you're interested in some gas lines that you know maybe in your data, you can go inspect the individual channels at the frequencies where you think the line emission could be, and see how the emission from the line changes as a function of frequency, and also combine those channels with line emission to get an image of that gas line. This flexibility means that just with one observation, because usually when you observe, you get both this continuum and gas lines with one single ALMA observation, you can get a lot of science done. And in the case of planet formation, these are some of the things that you can do. So if you're interested in the continuum, you can measure those masses, you can study the properties of grains, and you can use the structure of the continuum emission to infer the presence of protoplanets in these disks. If you have gas line observations, you can measure the amount of gas in the disk, but you can also derive the mass of the central object. And if you combine that with disk models, you can also derive the structure, the temperature structure, and the density structure of the disk. Of course, you can do a lot of chemistry, and you can also use gas line observations to infer the presence of previously undetected protoplanets in the systems. So let's start with the continuum. At ALMA wavelengths, when we observe the continuum, what we are seeing is thermal emission from millimeter to centimeter sized dust grains. And that means that when we look at an image like this, what we see is the distribution of millimeter, centimeter sized grains in disks. Now, we won't always have these high angular resolution observations, but that is not the only reason to use ALMA. ALMA has a very large collecting area, which means that it has very high sensitivity. So you can survey full star-forming regions and observe hundreds of protoplanetary disks in a few hours and get censuses of disk fluxes. And the interesting thing here is that sub-millimeter fluxes can be turned or translated into dust masses under some assumptions. So in this case, this is for the lupus region, and what you see here is the mass of the central source plotted as a function of dust masses. And you can clearly see this correlation between these two quantities that has been known for some time. But most of us are interested in the angular resolution of ALMA. And that incredible resolution has given us access to studying one of the main issues of planet formation theories, and that's the radial migration of dust grains. So when you start growing your dust grains in disks and they reach millimeter to centimeter sizes, they start feeling some drag from the gas in the system, and they start migrating inwards. And what that means is that the disks are usually much larger when observing gas than when observed in dust. Now, this radial migration is an issue because theory predicts that the depletion of large grains in disks is faster than the time it takes to form planets. So we really need to understand this, and ALMA gives us the tools to do that. We can observe gas, and we can observe the continuum at different wavelengths. So different wavelengths are sensitive to different dust sizes, and because this process depends on the grain sizes, with all this information and observations at different wavelengths, we can put all this and compare that with predictions from models. Now, luckily, ALMA also gives us access to the proposed solutions to the radial migration issue, which is dust traps. So when you have a pressure maximum in the disk, that is believed to retain large grains. And you will start accumulating millimeter and centimeter size grains, which can then grow to larger sizes and eventually form planets. One example of that would be this object of IRS-48, in which in orange, and it's a complete donut, the ALMA emission is plotted on top of it. That is mid-infrared emission from micron-sized dust. Whereas the ALMA emission, which is probing millimeter-sized grains, in green here, it's only coming from half of the disk. So what we think is going on in the system is that we have small grains distributed everywhere in the disk, but larger ones are accumulating this dust trap that hopefully will lead to planet formation. Now, dust traps don't need to be asymmetric, as in this case. We've seen many of them at the beginning of the talk. So rings and gaps can act as traps, and they prevent large grains from migrating inward and disappearing from the disk. So if you have observations at two different wavelengths, you can see how the spectral index of that emission is changing as a function of location in the disk. And that's important because the spectral index is connected to the grain size that's producing that emission. So this is TW Hydra. This is the continuum emission from two bands, band 6 and band 7. And this is the spectral index map. And you can see how the spectral index changes a lot if you're in a gap or in a ring. So that's telling us that grain sizes are changing as a function of radius in disks. So you can use this to study grain growth in protoplanetary disks. ALMA can also detect circumplanetary disks. So when you have a forming planet, we also expect it to have a disk of gas and dust around it. And this is the most famous example of circumplanetary disks. This is PDS-70. This is an ALMA observation, and you can see some blob here and another blob here. And when we observe this in the near infrared, we also see this emission from the same locations. If there's some system in which you think there's a planet, and maybe the planet is in a gap, so that you can detect emission from the circumplanetary disk, then ALMA may be able to detect it. ALMA can also infer the presence of undetected or unseen planets based on the shape of the continuum emission. So this is a beautiful ALMA image of HD 169142. This system has some central emission, this inner ring, and then a system of 3 outer rings. And this is a simulation. This is a hydrodynamic model in which they placed a mini Neptune and let the system evolve for some time. And you see how this planet reproduces and creates these rings that closely resemble the observation. So by doing this type of analysis, you can also try to infer the presence of planets that you would not be able to detect otherwise. Now, this is from the continuum side, but ALMA also observes gas lines. I've shown some of these images before. This is a very standard type of diagram when observing gas with ALMA. This is the CO line. That's the most usual line observing protoplanetary disks because it's the brightest. And what we see here is how the emission from that line is changing as a function of frequency. Now, why does it look like this? Well, if you think of a rotating protoplanetary disk, you're going to have some part of the emission that is not getting any closer or farther away from you because of the rotation, but then you're going to have some part of the disk that's red shifted and part of the disk that's blue shifted. So that's what we see here. This is the rotation of the disk, and the channels that probe the emission that's not red shifted at all or blue shifted would be these ones. And then if you go to red shifted frequencies, you will see this. Now it's getting more and more red shifted, and you get to regions of the disk that are moving farther away from you or faster. And the same goes for the blue line, for the blue shifted part of the line. Now you can combine all these channels to give you the zeroth moment or the total intensity of the line, and you can also weight the emission as a function of velocity, and you will get this rotation pattern of the gas in the disk. Now, all this has required no model so far, but obviously if you have a model, you're going to learn much more about the system. So with models, what you can do is you can use this rotation pattern that I showed before and try to match it with the rotation that you would expect based on the mass of the central star. That means that you can get an estimate of the mass of the central source without the need of any isochrons. And this is extremely interesting. You can use this type of measurements to tailor and to calibrate theoretical isochrons of young stars. And of course, if you have a disk model, you can also compare your model with your observations to infer the total mass of gas in the system, what the density profile looks like, and what the temperature structure is in the disk. Now, I was talking about CO, but there are so many lines that you can observe in protoplanetary disks. This is just one single example. These two thumbnails, those are continuum emission at different frequencies. This is the rotation pattern of the disk. But then all the other thumbnails are different molecules. You have the 3 different CO isotopologues. We have HCN, DCN, DCO+, N2H+. With all this information, you can study snow lines, which have a great impact on planet formation and the structure of planetary systems. And also, you can do this chemistry and study organic compounds. So if you're interested in chemistry, ALMA can get you really interesting data. Finally, for the gas, you can also infer the presence of unseen planets with gas observations. And that's because planets will perturb the local velocity field. So in this case, this is the continuum emission. And this is one of those channels of CO emission that I was talking about before. So you can build a model of how you think the gas would rotate in the system, and that would give you an estimate of what the emission would look like in this channel. And that is this dashed line. And you can see that here in the bottom part of the emission, that line is following the actual observation. But in the top part, there seems to be a kink here in the emission. It may be easier to see here. And the explanation for this is that if you place a 2 Jupiter mass planet here, it will create such a deviation from the planetless, let's call it, velocity field. So with gas observations, you can also detect planets that you may have been unable to detect otherwise. So that's the type of things that you can do with ALMA if you work on protoplanetary disks. I also want to mention that you can study the previous and the next stages of planet formation. So you can study class 0 disks or sources and try to see when protoplanetary disks form, which sizes they have first. And you maybe see how the size of disks changes as a function of age. Something that's very active at the moment is when do planets form? All this structure that we are seeing in protoplanetary disks, um, a lot of people attribute that to planets in disks, which means that planets have already formed. So we can go to younger objects. This is an example of a class 1 disk. This is 0.5 million years old. And in this case, they were already able to detect a system of rings and gaps that may be formed by planets. And also you can go to the later stages, debris disks, which are the remnant of the planet formation process. You can study the task composition and the structure of these disks. Here you have this beautiful ring from the Fomalhaut hot system. You can use multi-wavelength observations, maybe compare that with Hubble, or you could try to detect gas in the systems, which due to the high sensitivity of ALMA, is easily detectable in some debris disks. And with that, I think the only thing left is for you to write a proposal. So good luck.